Imagine waking up on an Earth where the skies are hazy with volcanic gases, the oceans shimmer a strange green, and not a single animal or tree exists. Billions of years ago, this was reality. Life clung on in the form of microscopic organisms, invisible to the naked eye. Yet, one of the most extraordinary transformations in Earth's history was about to unfold: the rise of oxygen. This event, known as the Great Oxidation Event, was not just a change in chemistry. It was a turning point that made our planet habitable for complex life, including humans. Without it, there would be no forests, no animals, no us. But here's the twist: the very oxygen that became our lifeline was, at first, a poison. In this documentary, we'll journey back over 2 billion years, exploring how tiny microbes triggered a revolution that reshaped Earth forever. We'll uncover deadly mass extinctions, radical climate shifts, and the slow but unstoppable rise of breathable air. And we'll connect this ancient drama to the very oxygen you're inhaling right now. So, sit tight. This isn't just ancient history. It's the story of how your every breath was written in stone billions of years ago. A poisonous beginning. Picture Earth, not as the blue and green planet we know today, but as a harsh, alien world. The skies were filled with volcanic smog, the oceans shimmered in rusty hues, and the air was utterly unbreathable. If you could step into a time machine and travel back over 2.5 billion years, you wouldn't survive a single breath. Oxygen, the very gas that sustains you, was almost completely absent. Instead, methane, carbon dioxide, and nitrogen ruled the atmosphere, creating a toxic brew that favored only one kind of life: microbes. These early microbes were survivors in the truest sense. They thrived in darkness, heat, and chemical-rich waters. But among them, a special group emerged: cyanobacteria. They were tiny, fragile, and unimpressive to the eye, but they carried a secret superpower: photosynthesis. For the first time in Earth's history, organisms captured sunlight and used it to fuel themselves. And in the process, they released something no one asked for: oxygen. At first, this oxygen was a trace gas, instantly consumed by the oceans and rocks around it. Iron dissolved in seawater reacted with oxygen, creating rust that sank to the ocean floor. Layer by layer, these banded iron formations built up, painting Earth's history into stone. Even today, miners in places like Minnesota and around Lake Superior dig up the remains of this ancient chemistry, unknowingly holding the first signatures of life's greatest revolution. But here's the twist: to most of life at that time, oxygen was not a gift. It was a toxin. Anaerobic microbes, the dominant forms of life, had never seen anything like it. Oxygen burned through their delicate cells like acid, disrupting their chemistry and threatening their very survival. Imagine a world where the air itself was poison. That's what oxygen meant billions of years ago. Still, cyanobacteria kept working, multiplying across shallow seas and releasing more and more oxygen. It was a slow build-up, taking millions of years. Like drops filling a vast jar, oxygen began to accumulate, first in the oceans, then creeping into the atmosphere. No one could have predicted it, but Earth was on the brink of its first planetary-scale catastrophe. What makes this part of the story so remarkable is how accidental it was. Cyanobacteria didn't plan to change the world. They simply existed, using sunlight to survive. Yet their waste product, oxygen, became the most powerful agent of transformation in Earth's history. It's as if microbes unknowingly flipped a switch that would alter the planet forever. By the end of this stage, Earth was no longer the same. The seeds of change had been planted. The atmosphere was beginning to shift. The chemistry of the oceans was rewriting itself, and the countdown had begun. Oxygen was no longer just a trace element. It was rising, slowly but unstoppably, toward a tipping point. And when that tipping point came, The world would never be the same again. The very gas that threatened life would eventually become its foundation. But not before wiping out nearly everything that came before. The Great Oxidation Event, the stage was set. Oxygen, once a trace gas, was now beginning to accumulate. For millions of years, it had been soaked up by the oceans and locked away in minerals. But eventually, those sinks could no longer keep up. What happened next is what scientists call the Great Oxidation Event, a planetary tipping point that forever altered Earth's destiny. Imagine the oceans first. They were rich with dissolved iron, giving them a strange greenish color. As oxygen levels rose, this iron rusted, falling to the seafloor in massive layers. These deposits hardened into rocks known as banded iron formations, alternating red and black stripes that we can still see today in the cliffs of Western Australia, South Africa, and even in the Lake Superior region of the United States. Every stripe is like a page in Earth's diary, recording the rise of oxygen across billions of years. But oxygen wasn't just changing the oceans. It was creeping into the atmosphere, too. For the first time, the skies above Earth began to carry measurable amounts of free oxygen. It didn't happen overnight. In fact, it took millions of years of relentless microbial activity. But the build-up was unstoppable, like water slowly flooding a valley. Once oxygen reached a critical threshold, Earth experienced one of the most dramatic turning points in its history. The air became reactive, reshaping the planet's chemistry. Minerals that had never existed before suddenly appeared. Rocks and soils began to rust on a global scale. Lightning in the skies now had new fuel, sparking different kinds of chemical reactions. For the first time, Earth began to look a little closer to the world we know today. Yet, with every gain came a cost. The very oxygen that transformed the planet also unleashed destruction. Anaerobic microbes, which had thrived for over 1 billion years, were suddenly exposed to an environment that was toxic to them. They began to die off in massive numbers, unable to survive in this new oxygen-rich world. It was, in many ways, Earth's first mass extinction event. From our perspective today, it's hard to grasp how devastating this was. Imagine 90% of all life disappearing, not because of asteroids or volcanoes, but because of something as invisible and intangible as the air itself. Entire ecosystems collapsed. Whole microbial communities vanished. And yet, through this destruction, a new path for life was being carved. Scientists often describe this period as a revolution in slow motion. Unlike the sudden disasters we think of, like the asteroid that ended the dinosaurs, the Great Oxidation Event unfolded gradually over tens of millions of years. But its impact was no less profound. It was the slow turning of a planetary dial, shifting Earth from one kind of world into another. By the end of this event, Earth's atmosphere contained oxygen for the very first time. The oceans had changed color, the skies had begun to clear, and the planet itself had stepped into a new age. But this was not the end of the story. Oxygen's arrival came with new challenges. Among them, a climate catastrophe that would freeze the planet from pole to pole. The Great Oxidation Event had transformed Earth forever. But its aftershocks were just beginning to ripple through the fragile web of life. Death and survival. The Great Oxidation Event was more than just a chemical shift. It was a planetary crisis. For billions of years, Earth's atmosphere had been oxygen-free, a safe haven for microbes that thrived in its absence. But when oxygen began to flood the planet, it was nothing short of catastrophic. For the vast majority of life, oxygen was a killer. To us, it's life-giving, but to those early anaerobic microbes, it was like acid, corrosive, deadly, unstoppable. Imagine being surrounded by something invisible that burned you from the inside out. That was the fate of entire ecosystems. Whole lineages of life vanished, erased in silence. This was Earth's first great mass extinction. But the destruction didn't stop there. Oxygen not only poisoned life, it also triggered a chain reaction in Earth's climate system, as methane, a powerful greenhouse gas, reacted with oxygen. It broke down into carbon dioxide and water. Here's the catch: methane traps heat far more effectively than carbon dioxide. With methane stripped from the skies, Earth's natural blanket vanished. Temperatures plummeted. The planet entered one of the most extreme ice ages in its history, a time many scientists call Snowball Earth. Imagine the entire globe, from equator to poles, locked beneath miles of ice. Oceans froze over. Sunlight reflected off vast white expanses, reinforcing the chill. It may have been the coldest time Earth has ever endured. And yet, life clung on. Not everything perished in this oxygen and ice catastrophe. Tiny microbial survivors found refuge in extreme environments: warm volcanic vents on the ocean floor, small pockets of liquid water beneath the ice, and chemical-rich environments that shielded them from the hostile New World. These survivors were tough, resilient, and adaptable, qualities that would define the future of life on Earth. Think about that for a moment. If these microscopic holdouts hadn't survived, we wouldn't be here. No forests, no animals, no humans. Just a lifeless, frozen planet drifting in space. Our very existence hangs on the razor's edge of microbial resilience billions of years ago. Meanwhile, Earth itself was changing. Ice sheets ground against the land, carving out new landscapes. Glacial melt carried nutrients into the oceans. The environment was harsh, but it was also resetting, preparing for something new. Oxygen wasn't just destructive, it was laying the foundation for a different kind of biosphere. In the United States, rocks in places like the Grand Canyon and the ancient formations around Michigan and Minnesota still preserve traces of these dramatic shifts. Layers of stone record alternating cycles of oxygen-rich and oxygen-poor conditions, a geological fingerprint of Earth's struggle between death and survival. Eventually, the ice began to retreat. Volcanic activity pumped carbon dioxide back into the air, warming the planet once again. The frozen world began to thaw, revealing oceans infused with oxygen and landscapes ready for transformation. Life had been scarred, reduced, and reshaped, but it had not been extinguished. Out of this crucible of extinction and survival, a new chapter of Earth's story was ready to begin, one that would set the stage for complex, multicellular life. The worst was over, and yet, the best was still to come. Oxygen had nearly destroyed life, but now it would become the force that allowed it to flourish. The rise of a new Earth. When the ice finally retreated and Earth thawed from its frozen grip, the planet looked very different. The atmosphere was no longer the suffocating blanket of methane it once had been. Oxygen, though still modest by today's standards, was now a permanent resident in the skies and oceans. The world had been cleansed, scarred, and reset, ready for something entirely new. This was the dawn of a transformed Earth. For the first time, the air carried enough oxygen to sustain more efficient metabolisms. Organisms that could tolerate or even use oxygen had a powerful advantage. Instead of slowly eking out energy through ancient chemical reactions, they could burn oxygen for fuel, unlocking energy on a scale never before possible. Think of it as moving from a candle to a roaring furnace. With this new power source, life could grow larger, more complex, and more diverse. It was in this environment that the first eukaryotic cells began to thrive. Cells with nuclei and specialized structures. Unlike the simple bacteria that had dominated for billions of years, eukaryotes were sophisticated, capable of more advanced functions. They were the prototypes of all complex life: plants, animals, fungi, even humans. Oxygen had made this leap possible. Meanwhile, Another invisible transformation was happening above our heads. Oxygen in the upper atmosphere began to form a protective shield, the ozone layer. This thin veil of gas absorbed deadly ultraviolet radiation from the sun, shielding Earth's surface from harm. Before the ozone, UV rays blasted the planet's surface, making life outside of water nearly impossible. But now, with this new protection, organisms could safely explore shallow waters and eventually dry land. On the seafloor, oxygen changed the chemistry of the oceans, unlocking nutrients like phosphorus and iron. These nutrients fueled bursts of biological activity, creating thriving microbial mats and, eventually, ecosystems far richer than anything Earth had ever seen. For the first time, life wasn't just surviving, it was diversifying. The rocks tell the story in ancient formations across the globe. From South Africa's Transvaal Basin to the Appalachian Mountains in the United States, scientists find signs of this biological explosion. Tiny microfossils and chemical traces reveal the first whispers of complexity, the opening chords of a symphony that would eventually crescendo into forests, fish, dinosaurs, and humans. And yet, it all comes back to oxygen. This once toxic byproduct of humble cyanobacteria had reshaped the entire planet. It had destroyed, yes, wiping out untold numbers of anaerobic species. But it had also opened doors. Oxygen wasn't just a gas anymore. It was the very currency of complexity. Every breath taken by a living creature was part of this ancient inheritance. By about 1.5 billion years ago, multicellular organisms, made of many cells working together, were beginning to emerge. They were still simple compared to the animals we know, but they were a radical departure from Earth's microbial past. The planet had entered a new era, where life would never again be confined to the microscopic. This was the rise of a new Earth, an Earth where oxygen wasn't just in the air, but in the story of every living thing. But the story doesn't end here, because what began with ancient microbes billions of years ago still shapes our future today. Why it matters today. It's tempting to think of the Great Oxidation Event as something locked in the distant past, a geological curiosity from billions of years ago. But the truth is, its legacy surrounds us every second of every day, every inhale you take. Every beat of your heart fueled by oxygen is a direct result of that ancient revolution. Without it, Earth would still be a barren world of microbes, locked in perpetual stasis. But the Great Oxidation Event is more than a story of survival and change. It's also a blueprint. By studying it, scientists gain insights into the forces that shape not only our planet, but potentially others across the universe. Here in the United States, researchers at institutions like NASA, Harvard, and MIT are using knowledge of the GOE to guide the search for extraterrestrial life. When we look at planets orbiting distant stars, one of the biggest signs scientists hunt for is oxygen in the atmosphere. Why? Because oxygen is rarely produced in abundance without life. The Great Oxidation Event showed us that biology can completely transform a planet's chemistry. Detect oxygen on a distant world, and you may have found a planet alive with its own story. Closer to home, the GOE also has lessons for today's climate challenges. Oxygen didn't just appear. It interacted with greenhouse gases like methane and carbon dioxide, plunging Earth into dramatic climate swings. Sound familiar? Just as ancient microbes reshaped the climate, humans are now doing the same, but on a far shorter timescale. The balance of gases in our atmosphere is delicate, and the GOE is proof of just how much a small shift can change the entire planet. Geologists in places like Michigan's Iron Ranges and the Grand Canyon continue to study rocks that hold the signature of this ancient transformation. Each layer of iron and sediment is a time capsule, preserving the exact chemical fingerprints of Earth's atmosphere billions of years ago. These rocks aren't just silent witnesses. They're teachers, offering clues about resilience, catastrophe, and renewal. And beyond science, the Great Oxidation Event speaks to something profoundly human, the idea that even the smallest things can change the world. Cyanobacteria were microscopic, fragile, and blind to the impact of their existence. Yet, through persistence, they reshaped an entire planet. It's a humbling reminder that transformation doesn't always come from the mighty. Sometimes it begins with the unnoticed. Today, as we face questions about our own survival, climate change, resource use, the possibility of life on other planets, the GOE gives us perspective. It shows us that Earth is not static, it evolves, it adapts, it resets. Life, too, is resilient. It can endure extinction, ice, and poison, and still rise again. So, why does the Great Oxidation Event matter today? Because it's not just history. It's a mirror, showing us where we came from and warning us about where we might go. Every breath of oxygen you take is a connection to a story billions of years old. A story of destruction, survival, and rebirth. And in that story lies both a warning and a hope. And so, the Great Oxidation Event was more than a scientific turning point. It was a survival story on a planetary scale. From poison to power, from death to life, oxygen shaped the destiny of Earth. Every inhale you take is a reminder of that ancient revolution, written across billions of years of history. If you found this journey fascinating, make sure to subscribe for more What If? Stories of Earth and the universe. Because the past doesn't just explain where we came from. It shows us where we might be headed.